Hello everyone, we're going to be talking about probability concepts. Some of you might find this very familiar, almost a review if you recently took statistics. Some of you, I'm sure, have not had it in quite a while, or you forgot everything that you learned in that class. So this may be a review, may not be. Either way, we need these concepts to go forward in this course. It also has a lot of practical application, as you'll see. I try to introduce practical things, everyday usages of probability statistics. So you can have feel like there's some relevance to the course, because it's probably difficult to see because you may not be in business yet. Okay, so let's start. This is really our laundry list of things we're going to do. They won't all be covered in this lecture, or in this recording, but it is the list of things that we will be covering. Different events and their probabilities, whether or not we're talking about an objective or subjective probability, the variety of different rules we have, and the concept of independence versus dependence. So again, those are just, you can check off while you're studying. Do I know what this is, when to use it, how to use it? Okay. So probabilities, as you may remember, range from 0 to 1, inclusive. 0 meaning it's not going to happen, like snow in Miami in August, and the probability that something will happen for sure. Okay, so all your answers have to be somewhere within 0 and 1, so it kind of is limiting, except there's an infinite number of numbers between 0 and 1. But we do like to have a frame of reference about where our answers belong. Just like when you go to the store, you know approximately how much your items are going to cost, so you know what you're going to have to pay or what you're going to charge. So numbers are not going to be greater than 1. If you come out with a probability greater than 1, then start over again. Erase and go, backtrack. Okay, so assigning probabilities happens in a couple of different ways: classical method, relative frequency, and a subjective method. So we'll talk about each one of those. We won't be doing the subjective method in this class because it's quantitative. Okay, we're looking for specifics here. We don't want someone's idea about something. You can't go to the bank with an idea. You can't go to Shark Tank. Oh, I had a dream last night. Okay, you have to show them the money. You have to show the numbers. So we'll be talking about classical method, which I call count and divide. We have relative frequencies because we like to know the probability of things happening, not the number of times they happen. We would like how often it happens. Okay, so let's move on to how we get along with each one of those things. So classical method, as I mentioned, is count and divide. So I'm going to count how many ways what I'm looking for can happen, and then I count and I divide by the total number of ways it could possibly happen. So if we just look at a die, okay, if we look at a die, we have 6 sides, no funny dies here, no Dungeons and Dragons or whatever, and we have 1 through 6 pips on each side. So there's a 1/6 chance of any side coming up because there's 6 sides. So if we want the probability of getting a 5, we would say the chances of getting a 5, there's only one. How many ways, not chances, how many ways can we get a 5? Well, the numerator says there's only one way. And how many total ways could we possibly get a 5? There are 6 sides on the die, so our answer is 1/6. Now we look at not 5. Now not 5 could be solved 2 ways. One is we could look at all the not 5s, the 1, 2, 3, 4, and the 6. Okay, those are 5 ways, okay, out of the total 6 ways that could possibly happen. The other way is to look at it as, terminology here, a complement. Complement means 1 minus. So if I have the probability of 5 is 1/6, not 5 is 1 minus 1/6. Okay, this one's very obvious. Later it's not as obvious, but it's extremely helpful to know when you have a complement. Okay, so now we have the probability of rolling the die and getting an 8. Well, here we have the answer for 0, because there's no way that that's going to happen. Now the probability of getting a 1 or 2 or 3 or 4 or a 5 or a 6 is 100%, okay, is 1, because this is the collectively exhaustive set of opportunities that we have when we roll the die. So one of those has to happen, okay? So that's why we have the 100%. All right, so there we have some little introduction of some of the numbers we're going to be working with. So now we look at the relative frequency method. So in this case, we see the number of times something happens, but we'd like to know a probability instead. Because if we're doing a survey of college students, we got 4,776 surveys that we handed out and collected, and we have 125 students answered the question, do you wear a seatbelt? And they said, 125 of them said never. Okay, well, when somebody says, well, 125 students said never, that's like out of how many? That doesn't help you any. You need to know what percent of the students said that. So if we want to calculate the frequency, we do the count and divide. 125 divided by the 4776. If we want the probability that they said always, we would take 2518 and divide it by 4776. It's really a method of doing count and divide. Okay, it's the means to the end here. Okay, so here we have all those count and divides that we did and all the probabilities. You also see if this is the collectively exhaustive set, all the probabilities, just like the dice, do sum up to 1. So if one of them were missing, you would just sum up the others, subtract from 1, and the one left over would be that probability. I mean, it happens all the time. We get some of them, but not all of them. Okay, a student just recently asked me a question. They thought there was something wrong with the problem because there were 3 events, but I only gave the probabilities for 2. Well, what the student forgot is that the sum of the events or probabilities have to add up to 1. So all the person had to do was sum up the 2 and subtract that value from 1 to get the rest. Okay, so in here we say, what's the percentage of respondents that answered always? Well, to get always, we did the 2518 divided by 4776, and we get the 5272. Now, sometimes we want cumulative answers. So here we want never or rarely. So we could do that 2 ways. We could sum up the total of number that say never or rarely and divide that by 4776. Or if we already had a table built, we could use the 2 values we already calculated and sum them up. Whenever you have an or, you will add. There are exceptions to that rule, but we're not there yet. When you or, you add. Dump after that. Okay. Okay, so now what if the question said, what percentage of the respondents answered something other than always? 2 ways again to do that. Something other than always means not always. So I would add up all the probabilities of the answers that were not always. I would sum all those up and I would get 47.28%. Now I did not just add those up in my head right there. I'm pretty good at math, but I didn't add those up. What I did is I used the second alternative. I said not always. Not always is a complement. So I have the value for always, and I just subtracted it from 1. So if I subtract 5272 from 1, I get 4728. Okay, so now we see the complement and how it comes into play when we don't have all the other numbers or we don't want to bother. And the more work you do, the more chance for error there is. Okay, so always look at a problem with more detail and depth than what you see. Don't just answer the questions that are asked. Always say, what else could be asked? What else do I notice here? Dig a little deeper in every problem. That's how you get an A. Go to SI, work with a TA, study with someone else, have the study buddy person, and see what you each see and work on the problem. If you both come up with the same answer, you're probably correct. Okay, so let's move on. And so here's the method that we don't use. Okay? This is not the one you could take to Shark Tank. So it's not measured. It's not a measured frequency. It's historical information. It's a degree of belief. Which horse is going to win? We don't know. Okay. Even, there's odds and everything for betting, but we still don't. We can't say with any certainty for sure. Same thing with any other kind of sports. Which team is going to win? What's the probability of a first down? Or all kinds of different subjective type things. Weatherman. They're close, but they're not always right. A lot of times we're not right, but when we have numbers to back up what we're talking about, we can make adjustments. We can say, oh, okay, or we can go back to the person who gave us those numbers. We're not always the person who does the computation. We're the interpreter. When you graduate from college, that's what you are. You're not the calculator, you're the interpreter. Okay, moving along to some of the rules now. Again, we won't do all of these in this recording because I'm going to break this recording up a little bit of this probability concepts. But we're going to talk about these first 2 rules right now, and that's mutually exclusive and collectively exhaustive. Later we'll get to the or. When you or, you add. When you do an and, you're going to multiply. When you or, you add and multiply. Chant that to yourself for a couple of days. We'll talk about conditional probabilities, which are extremely valuable, and the difference between independence and dependence and how to tell statistically which one it is and what kind of an impact it has on our problem. Okay, so let's go back to number 1 and 2. Okay, mutually exclusive, you can think about it as a personal relationship. If you're in an exclusive relationship, you were with only one other person. Okay, only one other person can occur, not multiples. All right, and that's the case here. So when we have a set of events, only one can occur. So the probability of passing and failing, it can't be both. That's why the probability is 0. It's not going to happen. It's going to be one or the other. Only one can occur. The same thing with probabilities, heads and tails. That cannot happen because it's not funny money. There's heads on one side, tails on the other. That's it. Win the lottery, lose the lottery. One or the other. You're not doing both, so the probability is 0 that you will both win and lose. If we throw a die, the probability of getting a 6 and a 4 is 0. We cannot get two numbers at the same time. All right? It's not all the numbers, but we're just asking for those two in particular. So like a 2 and a 3 or a 1 and a 6 cannot happen. Only one number can occur. Okay, let's move on to collectively exhaustive. Now here, it's not one and only. It's not just only one can occur. One has to occur. Right? We have to have the entire list of items that we're looking for the event we're looking at. So as far as a course is concerned, we have the probability of passing or failing. There's a 100% chance that it will be one of those. So that's why the probability is 1 or 100%. The probability of getting heads or a tail. Heads or a tail on a coin. It's a 100% chance. It's one or the other. You win or you lose the lottery. Well, that's only if you play. Okay? Once you're done with statistics, that's probably not something you'll be doing. Right? The odds or the odds of winning are very small, and your expected winnings, which we'll get to in a few lectures, is extremely small. So anyway, it's fun to daydream, but chances of winning are quite remote. Anyway, now we have that throw of the die, and now we're talking about the 6 or the 4 again. Now the probability of getting a 6 or a 4 is not 100%, okay, because it's not the collectively exhaustive set. Okay, the only way you can get it to be 100% is back to what we talked about 3 or 4 slides ago. It have to be a 1 or a 2 or a 3 or a 4 or a 5 or a 6. That's the collectively exhaustive set. Okay, so if that's not if 6 or 4 is not the collectively exhaustive set, and the 1, 2, 3, 4, 5, 6 is there another way of presenting a throw of a die that would be collectively exhaustive? Well, that would be here. This is another way. It's not always about just numbers. Okay, we can present different scenarios to mean something. In this case, what's the probability of getting an odd number or an even number? Because the odd represents the 1, 3, 5, and the even, the 2, 4, 6. That's all the possible outcomes that we could get. All right, so you might want to back up and look at those. And obviously, this is a PowerPoint that's on Canvas also. All right, so in the probability concepts module, this is module 1, just as a reminder. Okay, so now we're going to play like a little game. Like here's 5 different scenarios, and are they collectively exhaustive and or mutually exclusive? Okay, so we'll look at these 5 different situations. So if we have a coin and we flip the coin, what's the probability of getting the heads and the tail? Well, these are mutually exclusive. Only one can occur. So these are mutually exclusive events. They are also a collectively exhaustive set of events because heads and tails are the only things that we have. That is the complete list. And we saw that on another slide. The same thing with the next example where we're talking about a die. Here we're talking about 3 and a 5. Now they're mutually exclusive because you cannot get a 5 and a 3 on a die at the same time. The probability of a 3 and a 5 is 0. This is not a collectively exhaustive set because that would mean a 3 or a 5 would have to equal 100%, and it doesn't because we're missing the 1, 2, and the 4, 6. All right, so it's not the collectively exhaustive set. Now when we talk about a face card and a queen, that is not mutually exclusive because a queen is a face card. They happen at the same time. Right? Not mutually exclusive. Nor is this a collectively exhaustive set of everything in the card deck. Right? We'll see a card deck later on. Now we're looking at 2 dice that are rolled. Not 1 die, 2 dice. Now we either get the sum equals to 10, all right, or we get a double. So let's look at the first part and see, is this the collectively exhaustive set? The sum equals 10. No. Okay, there's lots of sums. There's 12, there's 7, there's 11. Okay, so there's a lot. So this is not the collectively exhaustive set. Getting a double. Can getting a double happen at the same time as something equal to 10? All right. So that can happen because a double could be the 5, 5, and that would equal 10. All right. So they're not mutually exclusive because more than these can happen at the same time. The two 5s, they do equal to 10, and it's not the entire set as we talked about earlier because the sums can be greater than 10 if you had the whole set. Now in the next one, the very first piece, sum less than or equal to 12, now we do have the entire set. So this is collectively exhaustive because we start with 6, 6, which is 12, 6, 5, which is 11, or 5, 6. Same thing. You got those are two different events. 6, 5 and 5, 6 are two different events. You have a green die and a red die. They're different. Okay, so they are collectively exhaustive. But now we're looking at getting a double. Getting a double kind of limits what we have, okay? Doubles can be double 6, double 5, double 4 in this case, but they happen at the same time as those sums. So they are not mutually exclusive, but it is the entire set of a possibility. Okay. So now let's look at the practical application of mutually exclusive and collectively exhaustive. Okay, this happens with surveys. So in this first survey we see here, they want to know how many times you eat out per month. Now if your answer is 3, which bubble do you bubble in? It's either here or here. There should be no or, okay? You can't have two things happening at the same time. You don't know which one to go. There's overlap here, okay? So this is not mutually exclusive. Surveys must be mutually exclusive, so you only have one place to go. Now in this survey, they want to know what your pre-tax income is. Well, it has most categories, except maybe the one you might be in while you're in college. You make less than $10,000. Let's say you make $7,500. What are you going to bubble in? It's not there. This is not the collectively exhaustive set, all right? They don't overlap, but they're not the entire set. We got everybody at the high end, but we don't have people at the low end, all right? So there's a reason why we need to have that. All right, so the next slide is going to bring us into the next topic. Okay, so it looks like this. This will be the beginning of the recording that's labeled Probability Concepts number 2. And we will start talking about a joint probability table, and we will use an entire deck of cards to start out, but then we'll narrow it down. So if you don't know cards, don't worry. I'll show you all that, okay? So this is the end of Probability Concept 1. I'll see you at the card table for Probability Concepts 2. Okay, bye-bye. Take care.